Hello dear students. Now let's begin with the next part of this chapter, that is electron pairing energy. Before that, just try to understand what do you mean by paired and unpaired electron. Now see here in this diagram, you can see that here in this electronic configuration, the electrons which are present in 1s orbitals, these are paired. They are having anti-parallel spin. Here the electrons which are present in 2s orbital, both the electrons are paired, but the electrons which are present in 2p orbital, there is a single electron in each orbital, and such electrons are called as unpaired electrons. So I guess now you understand what do you mean by paired and unpaired electron. Okay. Now let's define the pairing energy or electron pairing energy. Pairing energy of electron can be defined as the energy required to transfer two electrons with parallel spin into paired electron. Okay. And when the two electrons with parallel spin, they are present in two different orbitals, while when electrons get paired, they will remain in a same orbital. Here, these two electrons are unpaired. They are with parallel spin, and some energy is required to pair these two electrons. And when these electrons get paired, initially they were in different orbitals, but now they will occupy the same or one orbital. And here electrons, they will get paired and they will have anti-parallel spin. Here the electrons are with parallel spin. Here the electrons, they are cancelling each other's spin. Okay. So electron pairing energy is also known as electron spin pairing energy, as well as it is also known as energy of stabilization, and it is denoted by symbol P. So the energy required to transform two electrons with parallel spin into paired electrons. So this energy which is required, it is called as electron pairing energy. Okay. Now see here. Now let's discuss with the distribution of d-electron. D orbital, it can occupy 1 to 10 electrons. Okay. Now how these d electrons are distributed, that we will discuss. First thing, you need to keep in mind that the d orbitals are filled by electron according to following rules. The first and the utmost important rule, it is the electron will occupy the orbital of lowest energy. Second is Hund's rule of maximum multiplicity will be followed. That means electron will not pair up unless all degenerate orbitals contain one electron each. That is, they are half filled. Okay, let's begin with some examples so you will understand it easily. Now let us consider the filling of T2G. I guess now you remember what is T2G and EG. T2G and EG orbitals in an octahedral complex. In case of D1, D2 and D3. In case of D1, D2 and D3, electrons will occupy the T2G orbital only, following the Hund's rule. This filling will be same in strong field as well as in weak field. Here you can see in case of D1, 1 minute. In case of D1, only one electron is there. Now here I have shown T2G and EG orbitals blue line indicates T2G and red line will indicate EG orbital. Here, these T2G and EG, they are in strong field. So this distance is more, while here they are in weak field. So this distance is less, a weak field. Splitting is less. Okay. So in case of D1, D2 and D3, whether the electrons are present in strong field or weak field, they will occupy only lower energy level according to Hund's rule of maximum multiplicity. So whether it is strong field, one electron will occupy the lowest energy, that is the T2G. Same is for 2 electron and same is for 3 electron. These 3 electrons will present in lower energy orbital, whether it's in strong field or whether it is weak field. However, for D4 system, here for D4 system, occupancy of the T2G and EG orbitals, T2G and EG orbitals will be different. T2G and EG orbitals will be different in strong field and weak field. Now, see here in this diagram, here you clearly understand the distribution of D4 electrons. 4 electrons, strong field and weak field. Now, see here in strong field complexes, delta O, that is the splitting energy, is always greater than the pairing energy. So, as here splitting energy is more, the distance between the T2G and EG orbital is more. Electron, fourth electron, 3 electron, they will occupy the lower energy level, but the fourth electron, it will always prefer to pair up in the T2G orbital and gives the electronic configuration of the metal as T2G4. Here in T2G level there are 4 and EG 0. While so here in this strong field ligand, there is a pairing of the electron. So there are only 2 unpaired electrons. Such complexes are called as low spin complex. While when we go towards the weak field ligand, in weak field ligand, splitting is less. So this distance is less. That means here pairing energy is always greater than the splitting energy. And when pairing energy is more, but the splitting energy is less, the fourth electron, it always prefers to jump or occupies the EG orbital instead of pairing. So now we will get the electronic configuration T2G3, EG1, and all these 4 electrons are unpaired. That means in weak field ligand, we get 4 unpaired electron. More the unpaired electron, that means the high spin complex. So in this way, distribution of electron totally depends upon the whether it is strong field ligand or weak field ligand. Now, the similar explanation for the distribution of d orbital is very well explained in this diagram. Always remember one thing, for D1, D2, D3, okay, D1, D2, D3, as well as for D8, D9 and D10. The distribution of electron in 2G and E orbital is same, whether it is the strong field ligand or weak field ligand. The distribution is same. The difference in electron distribution will find only in D4, D5, D6 and D7 electron system. If delta O is greater than pairing energy, that means it's a strong field ligand, strong. And when the ligand is strong, splitting is more. So the electrons will always prefer to pair up. And when pairing is there, now see here these 4 electrons, they prefer to paired up here. While in high spin complexes or weak ligand field complexes, the splitting is less. So electron can jump in the orbital. Here there are only 2 unpaired electrons, but here there are 4 unpaired electrons. So it's the high spin. Similar case is observed in D5. In D5, in low spin, there is only 1 unpaired electron, but in high spin, there are 5 unpaired electrons. In case of D6, when the ligands are strong or in strong ligand field, all electrons get paired and it forms low spin complex, while in high spin complex, there are 4 unpaired electrons. Similarly, in D7, in low spin, there is 1 unpaired electron, while in high spin, there are 3 unpaired electrons. So you should understand whether the ligands are strong field or weak field, and based on that, the low spin or high spin complexes are formed, and the distribution of electron in d orbital, it totally depends upon the ligand field. So now here you can see distribution of 6 electrons in low strong ligand field and weak ligand field. See here, strong field ligand, strong ligand. There are 6 strong ligands are there and metal ion is. As ligands are strong, okay, so what will happen? Delta O value is always greater than pairing energy. As delta O is more, that means splitting is more, and if splitting is more, the 6 electron, they always prefer to get paired up. They don't want to jump in the orbital. All the 6 electron will get paired up in EG orbital, E2G orbital, and in strong field, what is the electronic configuration for 6 electron? Is P2G 6 EG0 is 0 unpaired electron. No unpaired electrons. In another case, if the ligands are weak, that means what? Pairing energy is more. That means splitting is less. If splitting is less, then 6 electron, they prefer to jump. So first they will feel 1, 2, 3, then they will go up 4, 5 and 6 electron will come here. So in case of weak ligand, the electronic configuration for 6 electron, it will become P2G4 EG2. That means there are 4 unpaired electrons. In strong ligand field, there were 0 unpaired electron, but in ligand field, there are 4 unpaired electrons. So it is the low spin complex, but this is high spin complex. So let's see the definition of low spin complex and high spin complex. Low spin complex is defined as the complex formed by strong ligand, that is strong field complex, have minimum number of unpaired electrons. So these complexes are low spin complex. The complexes formed by strong ligand have minimum number of unpaired electrons. So these are low spin complexes. While the complex formed by weak ligand, that is weak field complexes, have maximum number of unpaired electrons, are called as high spin complex. A simple thing, how you remember? Weak ligand, high spin complex. Okay, high spin means more number of unpaired electrons, and strong ligand is a low spin, less number of unpaired electrons. This way you can remember this. Thank you all of you.